For today's lesson, we will be going over method of joints. Let's look at some of the learning outcomes. First, we want to understand the method of joints and solve a method of joints problem using the procedure. If a truss is in equilibrium, the forces at each joint must be in equilibrium too. The force system at each joint in a truss is coplanar and concurrent. Truss members are straight and subjected to two forces, one at each end, equal in magnitude and opposite in direction. Let's look at member AB. If we look at the joints, then we see that there is a force AB and BA. At the end of the member, we have the same forces, but opposite in direction. The method of joints consists of applying the equations of force equilibrium at each joint to solve for unknown forces acting on the joint. Notes: always assume the unknown member forces to be in tension. Equilibrium analysis at a given joint can only be solved if there is at most two unknown forces and one known force. If there are not enough known forces, the support reactions must be solved first using the overall equilibrium equation. Let's take a look at a procedure on how to solve method of joints problems. First, identify your support reactions. Determine whether support reactions must be solved. Select a joint to start the analysis. Draw a free body diagram of the joint. Apply equilibrium equations at the joint to solve for unknowns. And repeat steps 4 to 5 for each joint in the truss until all member forces have been solved. Special cases of forces at a joint. First, we have two collinear members meeting at a joint. The forces in the two members are equal. Two non-collinear members meeting at a joint. Forces in the two members are zero when no external load is applied. Three members joined at a pin with two members collinear. Forces in the two collinear members are equal and the force in the third member is zero. Two pairs of collinear members are joined at a pin. Forces in each pair of collinear members are equal. The last case is a special interpretation of case 3. The third member force is equal to the applied force. Let's take a look at this example. Find the force members in members EF, KL, and GL for the Fink truss shown below. The angles are 30, 60, and 90 degrees. Let's identify our support reactions. At A, we have a roller support, giving us the reaction AY, and at I, we have a pin support, giving us IY and IX. Let's solve for our support reactions. First, we'll set up our positive axes. We will consider the entire truss and solve for the moment at I as it eliminates the most unknowns. Each of the members are at an angle, which means the vertical distance is 5 cos 30 or approximately 4.3 meters. AY is a negative moment and is 6 of the 5 meter panels away from I. Each of the external loads are positive. The 10 kilonewtons near E is 4 of the 4.3 meter panels away. The 20 kilonewtons at F is 3 of the 4.3 meter panels away, and so on. Solving for AY, we get an answer of 20 root 3, or 34.6 kilonewtons. Now we can select a joint to start analysis. I will be starting with joint A. Let's draw a free body diagram of the joint and apply our equilibrium equations. We will solve for the force in member AE. Using the summations in the y direction, we get an answer of negative 80 root 3 over 3, or 46.2 kilonewtons. Now, we repeat steps 4 to 5 for each joint. Let's look at joint E next. I will be shifting the axes to make it easier to solve. First, we will use the summations in the x prime direction to get the force in member EL. We will get an answer of 60 kilonewtons. Next, we will use the summations in the y prime direction to get the force in member EF, which will be helpful for analysis in later joints. Our answer will be negative 75.1 kilonewtons. We will now look at joint F. Here, we will use one of our special cases. Forces in two collinear members are equal and the third member is equal to the externally applied load. This will give us member FL as negative 20 kilonewtons. This will be used in future analysis. Lastly, we will look at joint L. We will use the summations in the y direction to find the force in member KL. Here, all the cos 30s will cancel out, and we will get the force in member KL as 40 kilonewtons. We will now look at the summations in the x direction to find the force in member GL. Solving this, we get an answer of 20 kilonewtons. To summarize our problem, we used the procedure to first find EF, which gave us negative 75.1 kilonewtons. Then we found KL, which was 40 kilonewtons. And lastly, we found GL, which was 20 kilonewtons.